Let's continue by computing HI from EI. To do that, we first of all write down EI. Direction, j hat. Amplitude, EYI. And the exponential part, the phasor term, e to the minus j phi I. Phi I is ki dot r. So what's left to do? Well, we need to know what ki is, and that's in terms of geometry, and then compute h. So let's look at the geometry for a minute. Ki is in this direction normal to the wavefront, and it's k1 times n hat. N hat is the wavefront normal, and we can see by simple geometry of right-angled triangles that n hat can be resolved into cos theta I hat and sine theta I k hat. Paying particular attention to the direction of n is extremely important in this. Remember, you're pointing in the directions always of increasing x and z, or some combination of decreasing, increasing. So you have to be sure that the SIGN that you pick for each of the components is correct. Let's now compute the cross product. This comes from Maxwell's equations for plane waves. HI is n hat ki cross ei divided by eta I. Well, we know what this is. We just computed it here from geometry. The E is given by this equation here. Now we just take a cross product. I cross j is k, and it has a coefficient cos theta I. K cross j is negative I, coefficient sine theta. This is the amplitude scaled by the impedance. And if we take the dot product of k with the r vector in 2 dimensions, our phase is k1 cos theta ix plus k1 sine theta iz. That's the phase. And now we have to do the same for the reflected, transmitted waves. And we'll do that and summarize all 6 waves on the next panel.